somber and grave subject. I would like to try something before we begin, if you don't mind. I was very much influenced by another person I saw on this stage the other day. So I would like you all to sit back and relax for a minute and project your thoughts to me. Project your thoughts. No, stronger, please. Stronger. Yes, I'm getting it. I'm getting it. Somebody over there is not thinking. Think harder, yes? I've got it. You're all interested in astronomy. It's a gift. All right, my self-introduction here. I am not a mentalist. It is not there. The one that I will focus on today, this is the last lecture, is I will focus on what my career was, that is health physics. It has been my experience that nobody in the audience will know what this means unless they are a health physicist or they are involved peripherally in that profession. Does anybody know what health physics is? One man there. Anybody else? Did I see any other hands? Anybody else know what health physics is? Okay, you're on the spot. What is it? That's right, radiation of the body, dose meters and all that stuff. So in layman's terms, it's radiation protection. What is the connection with astronomy? There's a lot of radiation in space, and indeed NASA used to have health physicists on staff. I don't know if they still do, with the contraction. It is something that would be very important for the Mars mission or for any deep space missions, well, deep solar system missions. Enough of me. If you came expecting me to talk about the Death Star, this is the wrong talk. We are not going to be talking about the Death Star, but rather the death of stars. So, audience, why do stars die? Does anybody know why stars die? They run out of hydrogen. Well, yes, that's the first stage. Essentially, they run out of fuel. And our star is no different. At some point in the future, it will run out of fuel. But don't worry, it's not going to be anytime soon. But there are some other things that will happen to our star, as I will discuss as we go on. Okay, so a star's life ends. What happens when the star runs out of fuel? Gravity takes over, and it is the gravity that defines how that star will collapse. It could be either in a supernova, it could be in a nova, which is a small version of the supernova, or it could simply just fizzle out if the star is really small. And you'll see some examples of that as we go along. It goes into a helium-burning phase, but it doesn't have enough gravity to initiate the next phase of burning, which would be carbon and so on up to silicon. And so what happens at the very middle of these is we form a degenerate carbon-oxygen core. And what do I mean by degenerate? It doesn't mean what you think it does. This is a very compressed piece of matter. The electrons and the protons the electrons from the atoms in the degenerate core are free to move around. This is a very compressed material. It is very dense material. Again, you'll see an example of this type of material when I talk to you about white dwarfs. This chart, which unfortunately you can't see very well, explains everything. It does. It explains everything from the birth of a star all the way through to its death and how it ends its life. And I could probably do the entire talk just referring to this, but because it is so fuzzy, we'll just move on. Okay. Inside stars, here's a distance for you. This is a big star. This is a supergiant. To put this in perspective, you'll see at the bottom of the slide there it says Jupiter's orbit. So, if that star existed as our sun, we would be inside that star, and the edge of this star would be where Jupiter is. And if you want to see Jupiter, you can actually see it. If you look up in the sky right now, it's a long way away, but you can actually make it out. In this particular type of star, you get all the burning processes taking place sequentially. So the first one is the hydrogen fusing, then you go into helium burning, fusing, then carbon, then neon, then oxygen, then silicon, and you finally get up to iron. And this is where that process stops. Iron cannot react inside a star, and when we get to the iron phase in a very large star like this, gravity takes over and there's boom. This is where the supernova comes from, in the very big stars, and we'll see that as we go on. So the hydrogen burning takes about 10 to the 7 years. That's 10 million years. About. These are approximate figures. Now, fortunately, that's a long time, because as we move down this burning process, these periods get less and less. The helium burning process is 1 million, so it's a factor of 10 lower. And then we get into the heavy element production, burning. So carbon's only 600 years, neon's just a few years, oxygen burning is only a year, and the silicon burning, which is at the end of the life of the star, is just 1 day. So it's really fast. So when we get into this phase, in terms of astronomical times, this is an instant. The star's going to go boom. What is this process that's going on? I think this is clear enough that I can explain it to you. So these are hydrogen atoms up here, and they are forced together because of the gravity and the speed and the heat that's going on inside the sun. And they will combine. Here we have energy being emitted, there's a couple of particles being emitted, and we are forming another material. This is heavy hydrogen, it's hydrogen 2. Another hydrogen comes along, there's more energy emitted, there's a gamma ray being emitted. Now we're forming helium. Helium can combine with another helium to emit energy and go back to hydrogen and also form another isotope of helium. So this process is going on, the hydrogen is being consumed, it is making helium. When this phase runs out, the helium will start to react with itself. Because a star is really nothing more than a big fusion reactor. That's what it is. It's a fusion reactor. The material in the star is the most common material in the universe, and that is plasma. It is the fourth state of matter. Mass loss. Now, stars are losing mass all the time. They're blowing stuff off. They're losing it in terms of energy because E equals mc squared, so energy and mass are equivalent, so it's losing mass in terms of energy, but it's also losing mass in terms of mass. The mass is being blown off, and this is the solar wind. The bigger the star, the stronger the wind. This is a picture of the effect of a solar wind. This is material being blown out of the star. The star's in the middle here. This particular one is a hot nebula. It's about 10,000 years old. And this is all from the solar wind, ejecting material. Our own sun is doing this as well. How much is our sun doing this? Well, the weight is given here. It is 10 to the 17, 2 times 10 to the 17 kilograms per year. That's a 1 with 17 zeros after it. That's a very large number. Fortunately, the sun is very big. You'll see by comparison, the weight is 2 times 10 to the 30th. So this is actually a very small loss in terms of what's there, but it is losing an enormous amount of mass in terms of an absolute number, and that's being just blown off by the force of the reaction in the sun. White dwarfs. White dwarfs are down here on the stellar chart. This is the main sequence of suns, stars. Our sun is there, classification G2. I talked about this on Life on Other Planets. These are the big, hot, short-lived stars. These are the smaller, cooler, longer-lived stars. And then they've got the supergiants up there. What is a white dwarf? How does a white dwarf form? This is at the end of a star's life. So for those stars that build up this degenerate core of carbon and oxygen, but don't have enough mass to initiate fusion in its core, become a white dwarf. So the helium burning keeps dumping this material into the core, but the core cannot ignite. So the fusion process stops at this place. The matter is degenerate, it is very compressed, it is very dense. How dense? Okay, here's some figures. So for something that is the size of our sun, its temperature will be about 25,000 degrees. The fact that that's degrees Kelvin instead of Fahrenheit or centigrade doesn't really matter at these numbers. It's quite hot. Its luminosity is low, however. It's 10% of our sun. And a teaspoon of this material would weigh about 16 tons. Teaspoon of this material, 16 tons. Well, of course, if you actually removed a teaspoon of this material from the star, it would become something else. It only stays in this state because gravity is keeping it in that state. If you removed it, it's not stable. So, if we had a chunk of white dwarf material the size of a beach ball, it would weigh more than the ship. Beach ball, weight of the ship. Try and visualize that. This is an artist's impression of mass transfer between a big companion and a small companion. And this mass transfer between the two stars can go one way and back again, and back again, and back again. It can actually oscillate. And we have an example that I'll show you later where we have recurring novae because of this mass transfer going from one star to the other. And there's a small explosion, and then some time passes, and there's another explosion. This is real, not the animation, but the existence of this binary system is real. It's in the constellation of Cancer. These two rotating stars are expected to merge in about 10,000 years from now. They're traveling at about 1 million miles an hour, and they are 1,600 light years away. One of the reasons this is being studied in great detail is it is expected that they might be able to detect gravity waves from this. This is something that is predicted from Einstein's theory of relativity. As yet, we haven't really found gravity waves, but we're looking. This is an example of two stars circling each other, and you'll see the mass transfer. Here's the smaller companion, here's the larger companion. This is now going into its red giant phase. This is at the end of the hydrogen burning process, and material is now being sucked out of the larger companion into the smaller companion. It is circling the smaller companion, it is heating up. X-ray beams are now being emitted along the poles of this. This does not go on forever because there is limited mass here. And you'll see that as the mass transfer continues, the star starts to shrink again, so that everything will come back inside the lobe that is controlled by that star's gravity. There is going to be a sudden collapse. When that collapse occurs, this process will also cease. That one there is now a white dwarf. And this star that went off is just a normal star that got fed for a while. And that is a process that will take millions of years. Right, let's talk about our own star, the Sun. It will eventually go red giant because the hydrogen will be consumed, will be into the helium burning process, and it will expand at that point. And this is the edge of the Sun. This is the Earth. In fact, the Earth will end up inside the Sun, as you'll see, but not to worry. We won't be around long before that. This chart shows you the ratio compared to our current Sun and the age in billions of years. This is where we are now. So this chart shows you luminosity, that is the brightness, shows you the radius of the Sun here.